Welcome back to a new video. In this video, I will look deeper into pseudo-random numbers. Now, pseudo-random numbers are in fact very important, but basically what we want to have are random numbers. And in a lot of applications, we are using random numbers. Now, random numbers are important in the sense that they can be used to create kind of simulations. A typical thing where we find random numbers is the roulette game. I already mentioned that in a previous video. And for example, when you are playing with dice, it's very important that for the roulette wheel, that every number has the same probability. Sometimes people try to find out if the roulette wheel is not well balanced, and they could try to find if there is a certain sector which would be having a higher probability than the other sectors. When they know that, they can start betting on that sector and they would have a better game against the bank. They caught some people in some casino. They were measuring with lasers, and the people thought that with the lasers they were trying to influence the roulette wheel, but basically what they were doing was measuring how the rotation is. Is there a preferential sector, yes or no? The same thing when you play with dice. Dice are made in a special way, the dice that you use in the casino, because every number should have the same probability. So if you are looking at throwing with a dice, every number has the same probability when you're throwing with one dice. Although when you're throwing with two dice, this changes some number combinations. For example, the number 7 has the highest probability, but that's only possible when both dice give a random output. So random numbers are very important. Some of you may remember the calculations like Monte Carlo analysis, and we also look at randomized algorithms where random numbers also are used. We developed, or people developed, random tables, and those tables can be used to find random numbers. You can use them in different analysis, but of course, when we're working with computers, we want to have the random numbers to be generated by a procedure. And that's what we're going to look at. Now, we cannot store those large amounts of random numbers, and therefore different ways have been developed to get random numbers. Now, unfortunately, these random numbers that are created by these procedures are not really random. And therefore, instead of calling them random numbers, we call them pseudo-random numbers. And we will have a look how to create these pseudo-random numbers. First of all, we have what we call the linear congruential method. This is one method that exists. There are other methods. And in the linear congruential method, we look at an expression like xn plus 1 is a times x index n plus c modulus n. And basically, this is the relation between the previous random number, x index n, and the next random number, xn plus 1. So basically, this is a relationship which will create a series of random numbers. Now, what do these different elements mean? First of all, xn plus 1 is, like I said, it's the next pseudo-random number, and they are between 0 and m, basically m minus 1, because the random numbers that we create can be equal to 0, but they are smaller than the modulus smaller than m. x0 is what we call the initial pseudo-random number. We didn't write it in this formula, but you can imagine if n is equal to 0, we have x index 1 is a x0 plus c modulus m. So x0 is the initial random number from which we start. We can select any number that we want. And of course, it complies with the same rules as the other random numbers. So it can be equal to or it's larger than or equal to 0, but it also has to be smaller than m. The next parameter, m, is the modulus, so this is what we have to select. C is the increment, and a is the multiplier, and a is larger or equal than 2, but smaller than m. So with these numbers, we can create a procedure in our computer how to calculate a set of pseudo-random numbers. Let's have a look at an example that we can show you. We look at the following number. The modulus is 13, the multiplier is 6, the increment is 4, and the seed is equal to 2. So we can start with the linear congruential method and say that xn plus 1 is 6n plus 4 modulus 13. So basically this is the expression, and we start with the first number, x1. So we find x1 is 6 times x0 plus 4 modulus 13. x0 is 2, so we find 6 times 2 plus 4 is 16, and 16 modulus 13 is 3. And now we use x1 to calculate x2. We find for x2, 6 times x1 plus 4, so we have 6 times 3 plus 4, which is 22. 22 modulus 13 is 9. We do the same for x3. We find at the end 58 modulus 13, which is 6. And for x4, we find the value 1. And we continue like this. So we continue the calculations, and when we look at a more completed overview of those pseudo-random numbers, we find the set we were in x4. x5 gives us a number 10, x6 gives us number 12, x7 11. Then we continue, and when we come to x12, we see that we find again 2. 2 is again the number x0. Now, since we have modulus 13, what we see, x13 is again 3. So we have a sequence of random numbers, but basically we only have 13 random numbers, and we continue with them. So after 12 occurrences, after 12 numbers, the sequence repeats itself again. Now, sometimes in some applications, we want to have a decimal number for the random number. So we can then divide the random number or the pseudo-random number that we have obtained by the module. So we find 3 divided by 13 and so on. We find different numbers in that case that we can also use to create more possibilities to create the calculations or to use the random numbers in our applications. Now, this is quite interesting when you look at it, but basically we are limited here to about 30 numbers. Now, when we take a modulus which is higher, we get more and more random numbers. Now, one of the elements that we can see, we look at some special cases and some issues. Now, in some cases, what we do or what the people do is to use the pseudo-random numbers with an increment c set to 0. In that case, we call it a pure multiplicative generator, and it can be written as xn index n plus 1 is equal to ax index n modulus n. The applications that can be used are in fact common, and in many applications what is done is that the modulus is set to 2 to the power 31 minus 1 with a multiplier equal to 7 to the power 5. Now this means that we create a larger series of random numbers, and we can prove that, or we can show that the number of random numbers we create is 2 to the power 31 minus 2. So these are in fact the number of random numbers, pseudo-random numbers that are being generated before they start repeating again. So basically, that is already a very nice overview, a very nice number of random numbers, but there is another issue. The linear congruential method is not in particular interesting when we want to do large simulations, because the problem here is that the method doesn't create a population of of pseudo-random numbers that miss certain important statistical properties of true random numbers. What we want to have is a set of pseudo-random numbers that behave like true random numbers. And with the linear congruential method, this is not the case. So there are other ways to create pseudo-random numbers, and those sets of pseudo-random numbers are in fact more interesting because they are more like the true random numbers. They have all the characteristics of the random numbers, and we can use those for more, let's say, for larger simulations. Now, that was the element about pseudo-random numbers. Very interesting to do the calculation. We can create a set of pseudo-random numbers. We can use it in some simulations. But remember that there are other methods than the ones or the one that I've shown here that can be used or should be used when we have large simulations. Now, this is the end for this video, and in the next video we will discuss the topic of check digits. So that was it for this video. I thank you very much, and I'm looking forward to seeing you in the next video. Bye bye.